Hey guys, today I'm going to talk about an interesting identity. This identity involves E, which is called the Euler's number, which is equal to the value down there 2.7182818284599045 and so on. That's an irrational number. And 2. Okay, so what is this identity? Okay, so it goes this way: E times the cube root of E times the fifth root of E times the seventh root of E times the ninth root of E, and so on. Now what do I mean by so on is that this goes on forever because you can see a pattern there, right? The pattern is that I'm taking every nth root of E where n is an odd number. Okay, so basically I'm taking every odd root of E in the numerator of this fraction, and this doesn't ever stop, so it goes on forever. In the denominator, I'm going to do something similar, except that I'm going to take every eventh root of E. So I'm going to take the square root of E, which is just the second root of E, times the fourth root of E, times the sixth root of E, times the eighth root of E, times the 10th root of E, and so on. Now this goes on forever as well. So I'm again taking every nth root of E. This time n is every even number. Okay, so now what is this massive infinite fraction equal to? Okay, because the numerator consists of infinite terms and the numerator and the denominator also consists of infinite terms. What is this entire thing equal to? Very interestingly, this thing is equal to 2. Okay, so it's pretty it's not an obvious derivation here. It's not quite obvious to someone when you just look at it. Euler's constant, you're taking every nth root and it's a fraction, and all of this is equal to 2. So how is this possible? Okay, so this has got something to do with the natural logarithm. So the natural logarithm is of any number is the value to which e should be raised in order to give you that number. Okay, so in simple term, if e to the power of x gives you n, then the natural logarithm of n is equal to x. Okay, so when you say what is the natural logarithm of 2, you're asking to what power should I raise e to in order to get 2. Okay, so it turns out that the natural logarithm of 2 is this value here, 0.693147 and so on. It's an irrational number, it goes on forever. Okay, so the decimal expansion of this does not ever stop. But what looks like a random arrangement of some random digits, it's actually not that. It can be written down in a very elegant way, in a very interesting way. What's that? You can write it down as 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on. Okay, so this also doesn't ever stop. So you keep adding and subtracting reciprocals of natural numbers alternatively. Okay, so you can express this even more elegantly as, let us say, the summation of n equals 1 all the way up to infinity minus 1 to the power of n minus 1 upon n. Okay, so that gives you this series here, the infinite series here, 1 minus a half plus a third minus a quarter. Okay, and all of that is equal to the natural logarithm of 2. Okay, you just have to remember that it is equal to the natural logarithm of 2. So now it's pretty obvious that e to the power of natural logarithm of 2 equals 2, because that's a pretty definition of the natural logarithm, that it's the value to which e should be raised, right? So it's a generalized definition that e to the natural logarithm of x is always equal to x. So we have already established that the natural logarithm of 2 can be expressed as 1 minus a half plus a third minus a quarter and so on. So if we will not be wrong if we write it this way, that e to the power of 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on is equal to 2. If you write it this way, it's actually not going to be wrong, because we have already shown, we already know that the exponent of e is the natural logarithm of 2 here. Okay, so it's just one of those cool properties of natural logarithm of 2 that it can be written in that way. Okay, that's just it. So using the rules of exponents, which we I believe we all learned in elementary school, that if you take like if exponents are subtracted, it means that the numbers are divided, the numbers with the same base are divided. So e to the 1 is just e, so e to the 1 minus a half means e to the 1 divided by e to the power of a half, and e to the power of a half is the square root of e. Okay, because this any number to the power of a half is equal to the square root of that number plus a third. So you're multiplying this by e to the power of 1 over 3, which is the cube root of e. Okay, because this is a generalized thing, that any number x to the power of 1 over n is it's equal to the nth root of x. So e to the power of 1 over 3 is the cube root of e. Similarly, minus a quarter. So what is e to the power of a quarter? Okay, there's the fourth root of e, and here again it's plus 5, so the fifth root of e, and this really it goes on forever. Okay, so you take turns multiplying and dividing, and if you accept that this thing over here, if it's equal to 2, then this is also equal to 2, because you're not really changed anything, you've just changed the way it is written. Okay, you've just written it as a fraction. Okay, so let us see if it indeed does converge to 2, because it cannot be equal to 2 at any point, because this is an infinite series, right? We are taking infinite products on both the numerator and the denominator, so they don't ever stop. So at no point is it actually going to equal to, but it's going to converge to 2. It's going to get closer and closer and closer to 2 the further we go down the line. So let us see. The thing about this is it converges pretty slowly. Okay, so I'm going to quickly do that. You can fast forward the video if you like. I'm going to go up till like a 15 terms maybe, I don't know, 11th root of e, 13th root of e, and let's go up to 20 e, 17th e. So I've taken every odd root of e on the numerator, well not every, but up till 19, and on the denominator let's do the same thing, the square root of e, which is, as I told you, is just the second root of e, and the fourth, the sixth, the eighth, the 10th over here, 12th, 14th, you can just fast forward the video, 16th, 18th root of e, and 20th root of e. Great. So it's equal to this guy down here, which is equal to that. It's 1.95184 approximately. So you can see that it's converging, right? It's getting closer and closer to 2, but see how slowly. I've taken 20 terms, and the best I could do is this. Okay, so it is going to take a lot of terms in order to get you anywhere near 2. Okay, but you can see why this is true, and the reason it converges slowly is because this series of 1 minus a half plus a third minus a quarter, that thing, it converges slowly. Okay, it takes some time to settle down at exactly 0.69314. So it wanders around for some time, and it takes some time to settle around that exact value of the natural logarithm of 2. And because that series converges slowly, this series, which is actually based on that alternative series, it also converges slowly. But of course, it does converge to 2. Now, the interesting thing is that both of these, the numerator and the denominator, they are something we call infinite products, right? And the most striking fact here is that neither the numerator nor the denominator individually do they converge to a particular value. They don't converge to any value. Both of them, they go to infinity. Like if you multiply the terms, if you multiply every odd root of e, or if you multiply every even root of e infinitely often, you're not going to stop at any value. You're just going to get infinity. And yet the ratio between these two infinities happens to be 2. How is that? Okay, and you argue with that. So the explanation here is that we are looking at it the wrong way. We are slicing this infinite series the wrong way. We are slicing this horizontally, right? We are separating the numerator and the denominator, which I think is the wrong approach, because if you do that, then if you start at the numerator and hope to reach the denominator, you will never reach the denominator, because the numerator goes on forever. So the explanation would be that we should slice this vertically. Okay, so the first term would in fact be e divided by the root of e, which is just the root of e, times the cube root of e divided by the fourth root of e, and so on. Okay, the third term is obviously it's going to be the fifth root of e times the sixth root of e, and so on. Okay, now that is going to equal to 2. Okay, and it's still an infinite product which goes off to 2, which gets really, really, really close to 2. I hope you guys enjoyed the video. If you did, just leave a like, and also let me know in the comments if you are aware of this interesting identity before. Thank you.